السلام عليكم ورحمة الله وبركاته. يسعد صباحكم يا شباب. اليوم إن شاء الله هنكمل بالمحاضرة اللي وصلنا لها المرة الماضية. وأعتقد إحنا وصلنا لهذا التوبيك computing the work from special processes, and I'll start first with the slide. So computing the work from special processes. Today we'll tackle 4 processes: constant volume process, constant pressure process, isothermal process, and polytropic process. And bear in your mind that work is equal, or boundary work. Boundary work equal integration of P pressure multiplied by dV, from V initial to the V final. Now, before going to those slides, I'll use the solving board, and we'll come to them one by one. So first, if we are talking about constant volume process, and let me draw the PV diagram. So here's PV diagram. If we are talking about state 1 to state 2, and both of them V1 equal V2, constant volume equal constant, so here in the x or V axis we can say that V1 equal V2. So if we start from V1 and we end up to V2, we are going vertically. So this is V1, and here we have V2. So V2 remain constant. So if we apply the integration, so integration equal to B multiplied by dV. So this one is constant, and this derivation will equal 0. So this value equal to 0. So there is nothing. The area even under the curve, there is no curve. We have point. And the integration or the area under it equal to 0. So for the first process, دائما الwork إيش تساوي? Always work equal to 0. So this is first scenario. Now let's move to the another scenario, which is constant pressure process. Constant pressure process. Constant pressure process. So here in this process, let me first draw the PV diagram. So constant pressure means B1 equal B2 equal constant value. Let us say here. And if we have expansion process from V1 to V2, so this is state 1, and because this is the V1, and then we'll move to V2. This is state 2. So if we apply the definition, this is equal to B dV. B is constant, will go outside the integration, then this is B delta V, because we are integrated from V1 to V2. So V2 minus V1, and we can say that this is B delta V, because this is point function. And here work either work or work from 1 to 2, because this is path function. So this is the second process. So second process, constant pressure process. The third scenario, or the third process, is constant or isothermal process. Isothermal process. So in the isothermal process, B multiplied by V equal to constant. Okay. So in the first process, V is constant. In the second one, B is constant. Here, multiplication B multiplied by V equal to constant value. Now, if we'll start with the definition, so W here equal to integration B dV. Or instead of B, so here, in terms of V, what do we have? Constant over V. So here in the integration, instead of V, I can substitute C over V dV. C refer to constant. Okay, instead of writing constant every time, I'll write it as C. Okay, so C will go outside the integration. So C, and we left up with integration from V1 to V2, 1 over V dV. So integration 1 over V will have C ln V2 over V1. Okay, or ln V2 minus ln V1, or we can transfer the subtraction to division. Okay, and instead of C, what we can write? So work equal, we reach up to here, C ln V2 over V1. Instead of C, I can write either V1 multiplied by ln V2 over V1, or I can write V2 ln V2 over V1. Okay, so this is the result of isothermal process. Okay, isothermal process. Okay, now if we have polytropic process, the last process. So process number 4, a polytropic process. So polytropic process, B multiplied by V to the power n equal to constant, where n here does not equal to 1. If it is equal to 1, then we'll go back to the previous process, isothermal process, because V multiplied by V to the power 1. Okay? So here B multiplied by V to the power n, where n does not equal to 1. So again, we'll start from, so the derivation in this part is required. Okay? So derivation is required. So if we need the equation of work, so work equal to integration of B dV, where B equal to, again, from this equation, constant over V to the power n. Okay, so substitute this value in the integration. So integration from V1 to V2 always will do the same. C divided by V to the power n dV. Okay, now here integration, so C will go outside the integration. Okay, so C integration V1 to V2, and Vn in denominator, I will bring it to denominator, so it will be V minus n dV. Okay, so integration for this value, what do we have? So C V minus n plus 1 divided by minus n plus 1. Okay, from V1 to V2. And this is equal, C V 2 minus n plus 1. Okay, this is multiplied by C minus C, so this C can go and you multiply it by two terms, okay? So this is V1 minus N plus 1 over 1 minus N, okay? So this is equal, oops, this is equal C V2 to the power minus N multiplied by V2 to the power N. So instead of writing the superscript minus 1 plus 1, I divide them, okay? Minus C V1 to the minus, and again the same, V1 to the power 1 over 1 minus N. So instead of C, I can write here, instead of this C, I can write V2 to the power multiplied by V2 to the power N multiplied by V2 to the minus N multiplied by V2 to the power 1 minus, instead of this C, I can write V1 from the definition, of course, multiplied by V1 to the minus N multiplied by V1 over 1 minus N. And this is equal, now this Vn with this Vn, if you multiply them, N minus N equal to 0, so V2 to the power 0 equal to 1. So we end up with V2 minus, and here the same, V1 over 1 minus N. So this is work for polytropic process. And the meaning of polytropic process, V multiplied by N equal to constant value, okay, where N does not equal to 1. Okay, let me go back now to the slide. So here are the four processes. Now the derivation step by step explained here. So this is constant volume, V equal to constant. Here you can see V1 equal V2. So the derivation or the integration equal to 0. So work at the boundary. So if we have constant pressure, V here is constant, as you can notice. Okay, constant value. So we can take V outside the integration, and we end up with V2 minus V1. So this is process number 2. Before proceeding, let us see this example. Okay, in this example, we have one fourth kilogram. So this is the mass of a gas contained within a piston cylinder assembly. Okay, and this is piston cylinder assembly. Okay, I'll assume them close assembly. And here we have mass of gas equal to one fourth kilogram. Okay, and this assembly or this system undergoes constant pressure process. So B is constant. This is the type of this process. We have constant pressure. Constant pressure process at 5 bar beginning. So B1 equal B2 equal constant value, and both of them equal to 5 bar. Okay, beginning at V or specific volume 1.2 meter cube. For a gas as the system, the work is minus 15. Okay, so work minus means work done on the system. So if the work done on the system means we have compression, I expect that V2 is lower than V1. Okay, so we'll see whether V2 is greater or smaller. It should be smaller because we have minus. Determine the final volume of the gas in meter cube. So we need volume. We don't need V or specific volume as C2. Let us move to the solving board. Okay. So what do we have? We have mass equal to 1/4 kilogram. Okay. The process is at constant pressure, so B1 equal B2 equal to constant value, which is this is kilogram, equal to 5 bar. And if I wish to convert from bar to Pascal, so every 10 to the power 5 Pascal give us 1 bar. Okay, so bar cancel out with bar, and we end up with 500 kilo Pascal. Okay, so this is given. Now another one thing given is the specific volume V1, which is zero point 0.2 meter cube per kilogram. Okay, meter cube per kilogram. Okay, so we need to find out V2. Now, how we are going to solve? Since we have and also something given, which is work from 1 to 2, which is minus 15 kilojoule. Okay, minus 15 kilojoule. So we need V2 in meter cube. Once we have constant process, then we can say for a constant process, W equal to constant pressure process, P multiplied by V2 minus V1. Okay. Now W given, which is minus 15 kilojoule, and this is equal. Pressure here constant, which is 500 kilopascal, and this is multiplied by. So this is multiplied by V2 capital minus. Now V1, the capital V1 equal to 0.2 multiplied by 1/4. Okay, and from here you can find out that V2 equal to minus 15 over 500, okay, plus 0.05. And please notice here that we have subtraction. So if you subtract this value from V1, so for sure this value will be lower. Then we have compression. Okay, so from here we can say that V2 equal to point, so to do the subtraction, 0.02 meter cube. Okay, now let's go back to the slides. Now the third scenario or third process is the isothermal process. In the isothermal process, here is the trend where BV equal to constant. Okay, so we'll start from the definition. Work at the boundary equal to derivation or integration from 1 to 2 B dV. But for ideal gas, if we have this is constant, then the whole here is equal to constant value. Okay, so BV equal to constant. So instead of every time writing MRT, okay, I write in the solving board C. Okay, so this go outside the integration, and we end up with 1 over V. 1 over V integration of this value equal to ln V2 V1, and we can write here constant or MRT. Instead of MRT, I can write BV. Either I write 1 1 or 22. Okay, so this is the result of the isothermal process. Now in the problem, either the problem we ask about derivation, do the derivation step by step, or you can start from the result. Either if we are talking about constant volume, constant pressure, or isothermal process, or polytropic. Now in polytropic process, we have V1 multiplied by V to the power n equal to V2 multiplied by V2 to the power n equal to constant value. Okay, so here we write constant. So yes, this is the relation for this polytropic process. Okay, so BV to the power n equal to constant. Instead of writing this equation in this format, we can write it like this in terms of pressure. Okay, so we'll start from derivation again, definition. And instead of pressure, I can write C over V n, okay, or constant. So if you continue the integration, we'll get this value, okay, or we can get this value if we consider n equal to 1. If it is not equal to 1, then this is the result. Because here in the denominator, if n does not equal to 1, we'll get this answer. If n equal to 1, then the integration of 1 over v equal to 1. So step by step, this is the step by step derivation. Okay. So here is the result. You can follow the steps one by one. So this is polytropic process, and here is the main condition. Now, if we assume, so far we have not assumed an ideal gas in this derivation. If we do, then instead of BV, I can write MRT2 minus MRT1, or I can take MR as a common factor. So this is equation for ideal gas undergoing polytropic process. Now, another type of mechanical work is the shaft work. So in the previous slides, we saw the boundary work. Now, shaft work, W shaft equal to force multiplied by the displacement, okay, multiplied by the distance or the number of rotation. So in terms of force, we can relate it to the torque, okay, where torque equal F multiplied by radius, okay, radius from the axis. Or we can write force equal to torque over R. So I can substitute the result in here instead of force. And instead of the distance that the shaft rotate, so we can write in terms of n, which is number of rotation, which is equal to, so n, the arc or the distance that the shaft rotate, equal to 2 by r, the parameter multiplied by number of rotation, okay, which is revolution. Okay, this one is revolution. Okay. So W shaft in joule equal to 2 by n, number of rotation, number of revolution, multiplied by torque, and torque here Newton meter. Okay, Newton meter. Its unit is a Newton. Now, if we have a very quick example, determine the power transmission through the shaft of a car. So here we have a shaft of a car, and we need the power transmission. When the torque applied, so this is torque, and the shaft rotate at a rate of 4,000 RPM. So this is N, or I can call it N dot. So if the previous equation we need it in terms of rate, then this is joule per second. And instead of revolution here alone, we'll write revolution per minute. Okay. So this is N dot means revolution per minute. So if we substitute, this is 2 by, okay, multiplied by number of rotation, which is 4,000 RPM, and this is because this one is in minute, so I'll divide by 60, so it will be revolution per second multiplied by 200. Okay, if you do so, you will get that this answer equal to 83.8 kilowatt. Okay. Okay. Let's see another example. So here we have a gas in a piston cylinder assembly undergoes an expansion. So he told me what will happen. So expansion volume will be in state 2 larger than state 1. For width, the relationship between the pressure and the volume is given to be Bv to the power n equal constant. Okay, so the initial pressure is 3 bar and the initial volume is 0.1. So since this is expansion process, then V2 must be greater than V1. Okay, and the final volume is zero point 0.2. So here 0.1 and here we have 0.2. Then this is expansion process. Determine the work for the process in kilojoule. So we need to find W and its unit kilojoule. Okay. For the first scenario where n equal to 1.5, so n equal to 0.15, that means we have polytropic process, correct? Because n does not equal to 1. Okay, because n does not equal to 1, it is 1.5. Okay, now n equal to 1, scenario B, this is isothermal process. Okay, now scenario C, n equal to 0, then this is constant pressure process, correct? Because V to the power 0 equal to 1, so we left up with pressure equal to constant. Let us solve it. Let us move to the solving board, and let me erase. Okay, so here what do we have? Scenario A, B V to the power n, where n in scenario A equal to 1.5, and this is equal. So if we assume that this is 1, then we'll have V2 to the power 1.5. And before doing so, let's remember what do we have. We have initial pressure P1 equal to 3 bar. Okay, and V1 equal to 0.1 meter cube, and we have V2, this is expansion process, then V2 must be greater, so 0.2 meter cube. Okay, and we need to find out V2, which is unknown. Okay, we need to find out V2, then we can find the work in kilojoule. Okay, so work is unknown. Okay, so if we have polytropic process n does not equal to 1, then work, here in this question he did not ask us to do the derivation. So we'll write the final result. So the final result, if you remember, B2 multiplied by V2 minus B1 V1 equal or divided by 1 minus n. So here we have n, we have B1 V1, and we left up with V2. So we need to find V2. From where we can find it? From the relation for polytropic. Okay, so the relation for polytropic, P2 equal to V1 V1 to the power 1.5 divided by V2 to the power 1.5. If you substitute the values, you will find out that B 1.0606 bar. If you convert it to Pascal, you will find out that this value 106.06 kilopascal. Okay, and now we are ready to find out the work from 1 to 2, which is equal to 10606 multiplied by, this is kilo, remember, okay, multiplied by V2 which is equal to 0.2 minus, so this is between brackets, minus B1 300 kilopascal multiplied by B1.1. Okay, between brackets again, divided by 1 minus 1.5, and the answer from this part equal to 17.576 kilo joule. This is work from 1 to 2. So this is scenario A. Now let's go to the other scenario, which is B. B, where in scenario B n equal to 1, and from here V1 equal V2 V2. But if n equal to 1, this is isothermal, so the isothermal relation for the work equal to V1 or any B multiplied by B, or V1 V2 multiplied by ln V2 over V1. Okay, so no need to go and find B2. Okay, so we can use what we have. So B1 equal to 300 instead of 3 bar kilopascal multiplied by V1, which is 0.1, multiplied by ln V2 0.2 divided by 0.1, and from here use your calculator. You will find out that work 1 to 2 equal to 20.8 kilo joule. Okay, let's go to the new page. So scenario C, if n equal to 0, then b to the power 0 equal to constant, and from here b1 equal b2. So if you have constant pressure process, then you go and benefit from the relation work, which is equal to B multiplied by B2 minus B1, which B1. No need to go and find B2. So this is time consuming. So instead of B1, this is 300 multiplied by B2 minus 2 minus, or 0.2 minus 0.1, and from here work equal to directly equal to 350 kilo joule. Okay. Now let's go back to the PowerPoint presentation. So this question done. So here the title of this example is evaluating expansion. Okay, expansion, pressure decrease and volume increase. Okay, example 3. In this example, We have a nitrogen as a working fluid. Nitrogen gas within a piston cylinder assembly undergoes a compression. So here we have compression means volume are going to decrease, but pressure are going to increase. Okay. So here what do we have? We have pressure 1 equal to 0.2 megapascal, V1 2.75 meter cube to state. So we are moving from this state and then we'll compress the gas up to V2 2 megapascal. Okay, the relation between the pressure and volume during the process is BV to the power 1.35 equal to constant. So this is what? This is polytropic process because n does not equal to 1. So if we have polytropic means we have pressure equal to V2 minus V1 directly. You can write the equation directly. Divide by 1 minus n. Determine the volume at state 2. So we need V2. We can benefit from the relation. Okay. N meter cube. Okay. And the work in kilojoule. So let me go to the solving board. Okay. Let me open a new note. So in part A, we need to find V2. Giving that V1 equal to 2.75 meter cube and V1 equal to zero point 0.2 mega Pascal and V1 equal to this compression. V2 will increase, so 2 megapascal. And as we expect that V2 will be lower than V1. Okay, and also he gave us the relation V1 to the power 1.35 equal to V2 to the power 1.35. So if I need V2, then V2 equal V1 to the power 1.35, okay, divided by V2, all of them, the power 1 over 1.35. Very important to know how to use or how to do this on your calculator. So B1 equal to 0.2. No need to convert because mega with mega will cancel out. Okay, this is divided by 2 multiplied by 2.75, okay, to the power 1.35. You can uh, multiply each term with this power, okay, so you will cancel the superscript of V1, or you leave it as is, 1.35. Then we have 5. Okay. So this is equal to 0.5 meter cube. Okay. Now, part B, we need to find out the work. So work for polytropic V2 minus V1 over 1 minus n. So V2 equal to 2 megapascal, 2 multiplied by 10 to the power 3 because he needs work in kilojoule. Okay, so this is now kilopascal multiplied by V2 which is 0.5, okay, minus 0.2 multiplied by 10 to the power 3 multiplied by 0.2, okay, divided by 1 minus 1.35. use your calculator, you will find out that this work equal to, because this is compression, then we have minus sign, minus 1.2 or 128.6 kilojoule. Okay, so this one is not 0.2, it is 2.75. So if you do so, you will find that this is the final answer. Okay, so that's it for this example. Now let's see this example before ending this lecture. So here we have a closed system consisting of zero point 0.9 kilojoule of air undergoes a polytropic process, okay, B1, V1, to a final state where B2, V2 given. So here B1, V1 given, and B2, V2 given. Okay, and he mentioned that this process is polytropic process. Polytropic process means B1, V1 to the power, or this is 1, to the power n equal to B2, V2 to the power n, where n does not equal to 1. But in this problem, he does not give us the value of n. Okay, determine the amount of energy transfer by work in joule for this process. So once we have polytropic process, means we have V2 minus V1 V1 divided by 1 minus n. Now everything is given, okay, except what? Except this value. So this value, from where we can get it? We can get it from here. Okay, we know everything except n here and in there. Okay, so I'll leave this question for you. You will find out that n equal to 1.31. Okay, and work this scenario because we have compression, so it will be minus 11.2 kilo joule. I will not solve it step by step, so try to solve it. And I need from you, okay, I'll give you a task, and I need the submission to be on Tuesday. It's not homework, it's not quiz, it is a task, okay, it is a bonus. So I need from you to solve this problem, okay, and submit it as a video. I need from you to capture or to record a video while you solve this problem step by step. So I will open a window on the Moodle, and I expect to submit a link, and inside this link you have to upload the video for solving of this problem. Okay, so then see you inshallah, and we'll continue with example number 5.